Today we're going to be continuing on the topic of species diversity. Yesterday we had spoken about the diversity of flora and fauna, but we focused very much on the question of how many species are there in a community. In other words, what is the species richness of that community? However, we did notice in passing that the abundances of species are not equal. So for example, if we were to look at this tropical forest in the Western Ghats, some species would be very common and other species would be rarer. This is true of almost any community that you would encounter, such as this group of marine fish that you see at a reef. There's, in this picture itself, there's some snappers, there's some emperors, and there's one single sweet lips. This would be true of mammals in the savanna, freshwater birds, any example. You don't need to go to some remote area to experience this. In a garden or in a park or anywhere in a city, you will find that some species are extremely common and others, many others are quite rare. So today we're going to be talking about species diversity in time and space. And the term diversity implicitly includes both the richness or the number of different types of species there are, as well as the abundances of those species. Now, as we did in the previous session, we're going to make some assumptions over here. We're going to assume that all species are ecologically equal. We're going to assume that all individuals are equal and that species abundance is recorded using appropriate and comparable units. Before we get into the issue of species relative abundances and associated indices of diversity, there are some simple ways to standardize species richness itself. Sometimes people use numerical species richness or the number of species per specified number of individuals, species density, the number of species per specified area, or as we saw yesterday, we can use rarefaction to overcome the problem of unequal sample sizes. These are rarely used because of the relationship between richness and abundance. Not all species are equally distributed or equally common or equally rare. Nevertheless, other indices have been used as well. Margolef's index D, which is the number of species minus 1 into log of the number of individuals. Menhennick's index, which is S by root of n, where in both of these cases where S is the total number of species and n is the total number of individuals. Historically, these indices were used because ecologists wanted to incorporate both richness and abundance, but none of these overcomes the problem of differences in the relative abundance of different species. So if one looks, for example, at the distribution of abundance of beetles in the River Thames, as you can see, very unequal distribution of individuals across species, and as in this case, the majority of species are represented by only a single individual, while very few species are abundant. A few species are abundant. Now, if we were to plot this, and these are some classic rank abundance plots. So essentially what you do is you plot the species with the most number of individuals first, and then the species with the next which is next in terms of abundance, and so on. And this gives us different models of species abundance both in theory and data. And there are different sort of preferred ways of plotting these different models. As you can see over here, at one extreme you get a geometric series which is extremely uneven, and at the other end you get a broken stick which is much more even. And we'll be talking about these in much more detail. Other ways of plotting this are also available, such as cumulative and relative abundance of these species. Now, there are different approaches to deriving a measure of diversity that combines relative abundance and species richness. One class of methods are parametric methods because these are based on the parameters of the distribution. And the first of these is the log series alpha. There's the log normal lambda, which is S0 or S star by sigma, which is S is the number of species in the class that has the most number of species, in the abundance class that has the most species in it, which is called the modal class, and sigma is the standard deviation of that distribution, of the log normal distribution. And there's another statistic called the Q statistic, which is the slope of the interquartile range of the cumulative species abundance curve. Now, all of these diversity measures, these parametric measures, are very similar, and the first two are derived from these distributions, the log series and the log normal, which we'll examine in much more detail when in the lecture on relative abundance itself. Today we're going to be focusing on how we derive measures of diversity given these uneven abundances. And these are the main parametric methods that have historically been used. Much more widely though, people have used non-parametric methods, and the most widely used of these comes from information statistics. It's known as the Shannon index. It was independently derived by both Shannon and Wiener, and appeared in a book by Shannon and Weaver in 1949. So it's been variously known as the, in literature you'll find it referred to as the Shannon-Wiener index, the Shannon-Weaver index, just the Shannon index, and so on. They all refer to the same thing. And the Shannon's index is essentially given by the sum of pi log pi, where pi is the proportion of individuals in the ith species. Now, there's an associated measure of evenness, which is h prime, or the Shannon's index, divided by h max. Now, let's take a look at what this actually means. So, for example, if I have sampled a community where I have recorded the number of individuals of different species, let's say I have species A, B, C, D, and E. I recorded 33 of this, 16 of this, 4 of these, and 1 each of these. Now, the total number that I have over here is 49, 53, 55, a nice round number, that's great. I can now calculate the proportion of each of these, the proportion of A, which is 33 by 55, proportion of B, proportion of C, proportion of D, and proportion of E. That's Pi, and then I can calculate log of Pi, and so on. And eventually, once I've calculated all of these, I would sum Pi log Pi. Since these are proportions, these will be negative, and to get a positive number, we take minus sigma Pi log Pi to get our Shannon's index. Now, the Shannon's index is going to be affected both by the number of species that I have. So, as the species richness increases, I will have a higher Shannon's index. But as you can imagine, the proportions of all of your species together will be higher if they're evenly distributed. So, in this particular instance, for example, out of these 55 species, if they were all evenly distributed, if they were all, for example, there were 11 of each of these, and there's 5 species, so obviously if they're equally distributed, the proportion of each of those species is going to be 0.2, right? So, the maximum value of the Shannon's index that I can get given any number of individuals if all of those species, given the number of species 5 or 10 or whatever it is, the maximum value of Shannon's index that I can get is if all of those were completely evenly distributed, which means that H prime would be equal to H max, and therefore evenness would be equal to 1, right? So our measure of evenness is derived in this case by comparing the index that we have obtained from our data to the maximum possible value that H could take, and that value would come about if all species were evenly distributed. So another commonly used approach to studying evenness is called SHE analysis, where E is taken as e to the power of H by S. H prime then is equal to log S plus log E, and so this is useful because it decomposes changes in diversity into components of richness and evenness. One of the problems with a lot of diversity indices, if you read a paper and you find a Shannon's index or the Simpson's index, which we'll talk about in a minute, is that you look at that number and you don't know whether that number is high or low because of high richness or high evenness. And so it's useful to be able to decompose your components of diversity into richness and evenness. So the measure that we just mentioned, the dominance measure of the Simpson's index, is essentially D is sigma of pi squared. It's usually expressed as 1 minus D or 1 over D. There's an associated measure of evenness, which is 1 by D by S. Now, the Simpson's index, because it doesn't take logs, tends to be influenced by the most common species in the community. What this means is that if you have again a similar distribution such as this, species and individuals, you have the same 5 species. Let's take the same numbers, 33, 16, 4, 1, 1. Now, when you use the Shannon's index will be sensitive to changes in the numbers of even the rarer species, or even if you add a rare species. The Simpson's index tends to be influenced very strongly by what happens to the most common species and perhaps the second most common species. Adding a few rare species or removing rare species or changing their abundances, because those proportions are so small, tend not to affect Simpson's index at all, because it's simply pi squared. The largest values contributing to your index are the ones that come from the species that have the highest proportions, right? And so it's sensitive to changes in those species, and that's why it's known as a dominance measure. So these are the two most common indices of diversity that are used. There are others as well, but we won't spend too much time going into that. These are available in any textbook on diversity. So those are the common measures of diversity, and though others have been used, we're not going to go into those today. However, it is useful to think about what these measures of diversity should accomplish, and Smith and Wilson provide a guide to this. The requirements of an index, they say, is that it should be independent of species richness. The measure decreases if abundance of the least abundant species reduces, that is, the community becomes more uneven. It increases if a rare species is added to the community, and it's unaffected by the units used to measure it. They also put down a set of desirable features, that it should have a maximum value when abundances are equal, a minimum value when abundances are as unequal as possible, that the index shows a value close to minimum when evenness is as low as is likely in a natural community and not just a hypothetical extreme, and that minimum is attainable with any number of species, intermediate values for intermediate evenness, and the measure should respond in an intuitive way to changes in evenness, and that it's symmetric with regard to rare and common species, and skewed distributions should lead to lower values of the index. So they'd sort of put these down as a set of features that were desirable for an index to be a good representation of both richness and evenness in a community. You'll find a table where they've evaluated a number of evenness measures, and many of these fulfill some of them fulfill all the requirements, and some of them also have many of the desirable features. So this is something that you might want to examine more closely later if you plan to use an evenness measure. In general, in community studies where abundances are taken into account, one of the approaches is to report species richness separately, because that, as we've discussed, is an important trait of communities, and then to use one of these measures of evenness independently of that to or additionally to it to illustrate the degree of evenness, or the way in which abundances are distributed across that community. Now, we've talked predominantly about species diversity. We said we would focus on this, and with the caveats that we sometimes don't know what we might not be able to identify all species with confidence. We struggle with species concepts. Despite all of this, a lot of the work on diversity, in fact, a majority of the work on diversity focuses on species diversity. But there are other forms of diversity as well. One of these is taxonomic diversity, and this is based on the idea that taxonomically varied assemblages are more diverse. So if you look at a phylogenetic tree, there are some of these are more closely related to each other. There are some that are more deeply divergent, and we can use the topology of the phylogenetic tree. Daniel Faith came up with a measure of phylogenetic diversity where he summed branch lengths within a taxonomic tree to examine variation in taxonomic diversity. At the broadest level, I think where the principle is that a particular lineage, or what we might call a species, might be more or less unique than others. And to take a sort of very extreme example, going back to the comparison of snakes and tuataras, in your group of reptiles, the group of tuataras is represented by a single, again, or two species, depending on which sort of taxonomy you follow. That represents the entire evolution of that group over 200 million years. Snakes, on the other hand, have 4,000 species in about 130 to 140 million years. So that the evolution of that lineage in 100 plus million years is represented by 4,000 individual species, whereas this other one is represented by a single or two species. And from that perspective, one argues that tuataras hold a lot more evolutionary history than any single species of snake might. Now, that's a very deep sort of divergence, where often in communities we're often comparing species that are much more closely related. So for example, this relatively newly described species of frog, Astrobatrachus couricciana from the Western Ghats, is again a single species of this genus, belongs to its own family or subfamily, and one of its closely related groups, as supported by current phylogenetic trees, is a family called Nyctibatrachidae, within which the genus Nyctibatrachus has over 40 species. Nyctibatrachus has another genus called Lankanectus, found in Sri Lanka, which has just a couple of species in it. And in comparing these, even intuitively, it seems that we should have a way of accounting for the fact that Astrobactericus or Luncarnectus carry so much evolutionary history relative to any single species of the genus Nyctibatricus. So the way that this is done is by using measures of taxonomic diversity, which takes into account species abundances and measures the average path length between two randomly chosen individuals. And taxonomic distinctness, which is a special case of the above, where each individual is drawn from a different species. So taxonomic distinctiveness is the average path length between any two species, and diversity is the average path length between two randomly chosen individuals in the community. It also takes into account, therefore, the commonness and rarity of species. These are independent of sample size and species richness of the sample. Visually, we can look at these relationships on the right and left, and in case A, so if you look at this as species, genus, and family, and likewise here. What we can see in case A is that every species over here, each one belongs to its own family, right? In this case, all of them in fact belong to the same genus and obviously the same family. And therefore, the evolutionary history that's carried by every species in case A, because it belongs to its own family, is substantially more. You might have morphological divergence. You would definitely have far more genetic divergence. You might have ecological divergence. So, in some sense, the evolutionary history, or from an information statistics perspective, the amount of information carried by each species is greater in case A than in case B. One can take a slightly different example where, if we were to look at the comparison between C and D. Now, you have this case where in both cases there are two different genera. They all belong to the same family, but in case C, the species are evenly distributed across the two genera. In case D, there's only a single species in this genus. As in the case above, where the diversity or taxonomic diversity of A is greater than B, the taxonomic diversity of C would be inferred to be greater than that of D. One way to look at it, again from an information theoretic perspective, is if one were to randomly sample species in both these communities, in any given sample, I'm likely to have representation from both genera, whereas in any given sample over here, more often than not, I'm going to have samples belonging to a single genus. There are other measures of diversity as well. We touched briefly upon functional diversity. We could use, one of the ways to measure this is using a dendrograms constructed from species trait values. But in ecology and evolution, there's various other traits that have been used to understand ecology and the evolutionary history of lineages. Body size is one of these. Species abundance has been used as a surrogate for resource use, but the body size abundance relationship can also be used to derive an index of diversity. Finally, once we've derived these measures of diversity, we are often in a situation where we want to compare these measures, because our question might be, why does forest A have more species of trees than forest B? Is there a latitudinal gradient in species richness? Are there more species towards the equator than in temperate areas, at lower latitudes than higher latitudes, at lower elevations than higher elevations? And so these single measures, if I come up with an index, a Shannon's index that is 3.4 for one forest and 3.7 for another, those two numbers by themselves statistically don't give me enough information to compare them with each other. So often we need to calculate variance and associated measures such as standard deviations and confidence limits. And in order to do this, we might need to generate distributions, which is to say that what's the frequency distribution of diversity that I might get from forest type A, and what's the frequency distribution of forest type of diversity that I might get in forest type B. One of the ways of doing this is using bootstrap and jackknifing resampling procedures. So we can subsample our actual data, and using those subsamples, we actually generate multiple values of diversity or of any particular index that is of interest to us, or species richness itself, and that distribution of values allows us to calculate variance and confidence limits. We can then use these resample data to compare groups using either parametric or non-parametric tests to arrive at inferences about the ecological questions that we started with. In closing, I would revert to the reason that we're doing this. We don't calculate these indices in a vacuum. Our goal here is to understand, some mechanism that underlies these patterns, and so it's really important to be explicit about the questions. The questions then help us determine which particular index of diversity, or richness or evenness is going to answer that particular question, and then we need to use appropriate quantitative methods to statistically determine whether those patterns are supported by the patterns and mechanisms are supported by the data that we've generated. So that will be it for today. Thank you, and I'll see you again soon.